channel my inner motion. Keep trying.
Yes, so after Loris tried his inner motion, you'll have to practice. Yeah, that's right. It's okay, but it takes
a few more steps.
Exactly. So we continue with our afternoon session, and Loris will tell us how to verify many programs at once.
Many.
Many.
Okay.
So it's doubly exponential.
It's infinite exponential, so it's a tower. Okay, am I good? Okay, sounds good. So just like this was work done when I was in Madison, great times there, and as of 2 days ago, I'm now in San Diego. I'm here, but I'm in San Diego. But yeah, so that's it. So you all know this. This is a Hoare triple. You want to prove that this program, when we run it on the inputs that satisfy P, gives us an output that satisfies Q. Sometimes you write it like this. Applying S to everything in P gives you a subset of Q. Okay, we like that. Today we're going to do this. So we have a new type of triple. I want to get things that satisfy P, and if I run any of these programs, I get something that satisfies Q. I have a set of programs. So for every SI in this set, I want to verify them all. So this is in LaTeX. These were attached here, but for a PowerPoint, I couldn't put them there. So it was just pretend that it looks like this. It's just a different triple. This is what it looks like in the paper. Okay, but maybe bars is because it's a set, so we count them or something. I don't know. Anyway, but it's a different symbol. Okay. And you might want to ask, why do we need to do this? Okay. So here is the reason. So this is happening. It was my first, I guess, PhD student, depending on how you count. And so the first problem I gave him, it was like I used to work on transducers and automata and stuff. And one of the things we used transducer for was to verify that string encoders were correct. So this is an implementation in a very low resource language that I only used of base 64 encoder. And you can write a decoder for it, which is the program that does the opposite of the encoder. And my point was like, why do you need to write both? Once you write an encoder, there is only one decoder. Like this is an injective function, it's total. So we try to synthesize it. And that's the first thing Happy did was to basically take this big program synthesis problem and reduce it into synthesizing smaller programs here that you don't need to understand. And so for those small programs, we could call Cygos solvers, which at the time Cygos was starting to be popularized. And so we say, OK, let's call Cygos solver. So given this, we want the inverse of this little thing. You don't need to understand what it is. So we try one solver, E-solver, which was actually the very first winner of the very first competition on Cygos. And it gave us what we wanted. It was kind of a simple expression that says end of a bunch of things. And then we called, at the time, the implementation of CVC4, which is kind of then won all the competitions. And CVC4 will give us this program. Okay? So you don't need to understand this program. But this program basically says, if the input is 1, the output is 3. If the input is 2, the output is 7. If the input is... So it was correct on all the bit vectors that we were considering, but it was slightly verbose. So we didn't like this. So then Happy, which at the time was very happy, became very, very sad because it basically really wanted the small solution. And so this is that came from the E-solver. That was the solver that one of Rajiv's students wrote as part of the... So they're both Cygos problems. They say the same thing, but one gave us a solution which was correct but small. One gave us one that was correct but big. So then Happy became very sad with the power of LLMs. And then he became happy again because he realized, oh, can be my PhD. I can figure out how to solve the problem of finding the best program. OK, so he started working on this. So his first paper that he wrote after this was this thing called Q-Cygos, which is just Cygos plus quantitative objectives. It's just a format. But he also came up with an algorithm for solving this. And the algorithm is very simple. It's linear search. So you start with, you have a search space of possible programs, and you have the correct programs. OK? And now you get one program in this space, using your favorite Cygos solver, and you declare victory. But now you ask, is there a better one? Is there one that is, in this case, that says uses fewer if-then-else statements? And so you restrict the search space to only consider programs that are better. And we don't need to understand how to do this for this talk, but you can write a grammar that does it. That was what the paper showed. And you can keep doing this, and you can keep doing this. Basically, your search space, it says better and better and better. And at some point, you found the best. And so you're very happy. Except that, how do you know it's the best? Well, you have to prove that there is no better one. So you need to show that in this search space, there isn't a solution. And this is, we are familiar with, is the problem of proving unrealizability in program synthesis. So when we got to this point, when we called any of the solvers, we really wanted the proof that no program exists. And instead, we were getting timeout, fail, or not terminate. Because the solvers, all they were doing was enumerating all possible programs or searching, but they didn't have a way to say all these programs are incorrect. Sounds like a verification problem. So that's what it is. So basically, we're trying to prove unrealizability. And what we're trying to prove is that for every, so usually this is given to you as a grammar of programs. You want to prove that every program accepted by the grammar, at least on one input, is incorrect. OK? So unrealizability is like we have all these programs. There are infinitely many. You want to show that all of them on one input are incorrect. And the input, the problematic part here is that we have to reason about many programs, in fact, infinitely many, all the programs in a grammar. And the input falsifying the specification may be different for all programs. Yes?
But you're trying to prove that something is optimum, right? You only need to consider smaller programs.
Correct.
And now that's a finite space.
No,
Why
smaller,
not?
Yes, but fewer if than else is infinite. In fact, that's the next example that you asked. So let's try to prove that the max of 2 number can be implemented with less than one if then else statement. This is the grammar, OK? This grammar is infinite, has infinitely many programs. So not all quantitative objectives are size. That's kind of the point. So the goal here is that the framework I didn't talk about allows you in arbitrary way to specify quantitative objectives. And one that you can specify is size, for which the problem is easy. In fact, for that, CVC5 will work. But sometimes you want to say, oh, you gave me max with one if then else. Can you do it with less than one? Or you gave me a circuit with 6 ends nested. Can you do 5 ends nested? So in that case, what you get is that it's an infinite search space. And in this case, you can convince yourself that you cannot implement the max of 2 numbers using a program in this grammar, because these are just linear expressions. You basically can say ax plus by plus c. And so it's an infinite set, so we need to prove them all. And the challenge, as I said, that the falsifying input can be different across different programs. So in this case, here are 3 programs, x, y, and 1. These are all wrong. They're not the max of 2 numbers. But they're all kind of wrong. They're right on 2 inputs and wrong on the other one. OK, so you need to understand this. And in this particular example, once you get to 4 examples, actually, you get that every program is wrong on one of the 4. It's kind of related to VC dimensions and mistake bound, but that's irrelevant here. But the point is that there is this challenge of how do I prove properties like this? How do I prove that all these programs are wrong? OK, so going back to what we said before, I have a set of programs, I have a precondition, and I have a postcondition. And the way this relates to unrealizability is that I'm basically trying to prove that if I negate the specification, so I'm taking the not being right, that's what I'm trying to prove, is that every program, when executed on the inputs, is not right. So this is similar to how you use hard logic not to prove that something good can happen. You prove that something bad cannot happen. OK. Let me give you some other applications beyond unrealizability. So this is my dream. So if you want to work on something hard, this is a hard problem for formal Methodists and people that do SAT solvers. So what I was really after when I started working on this, I want to do CDCL for program synthesis. So what is CDCL? I run a SAT solver. I get stuck somewhere. I build the proof of why I got stuck, of basically why this is not going to work. And that proof is reusable in other places. How can I do this for synthesis? So in synthesis, usually you enumerate, like in SAT. You build programs. And then at some point, you get at a place where basically no matter what you put here, it's not going to work. And so what we were trying to do here is to build these proofs so that we can reuse them later in the synthesis process. So that's one potential application. This is another interesting application. So if you're running, for example, if you're trying to verify JavaScript code or code where there is a reflection or you're allowed to load dynamically other code, really verifying this program boils down to verifying all the completions of this untrusted string. So eval is basically this interpreter that can take a string as code and run it. So in this case, I want to verify that no matter what I put here, this triple holds. So that's another application of this potentially. OK. Questions about the setup? Let's verify lots of programs. So this was the first thing we did. And this is the kind of the most important lesson in research. First, try the easiest thing. So we tried the easiest thing, which was we had this, in this case, let's say we have a Cygos problem. where the specification, let's say, only uses finitely many examples. So these are 4 examples that encode max. So the max of 0 and 1 is 1, the max of 0 is 0 and 0. And what we did is that we built a C program with an assertion, and I'm going to show you how to build that program, such that this verification problem is such that the assert always holds if and only if the problem is unrealizable. So my first solution is to use something that already exists. So let's see how we do that. And this is actually educational in a way. And here is the idea. So let's say I have one input. X is 1 and Y is 0. And I want to show that all the programs that I can derive from start will produce the wrong output. So this is the for now, just it's a magic that is going to run x0, y0 on some program in the search space, return an output. And what I want to show is that the output is wrong. So if this assertion holds, it means that the programs in my search space, they're all wrong, which is unrealizable. So basically, this is saying, take those inputs, run them non-deterministically on one of the programs. If the output you get is always wrong, none of the programs is right. And the idea here is very simple. You can just use non-determinism to basically guess which production of the grammar you're going to use. So in this case, this is the grammar we had before. It is 0, 1, x, y, and plus. So you say, oh, I non-deterministically return 0. That's the production. If I choose x, I return the x component of my input. And if I choose plus, I'm going to recursively build basically run 2 subprograms and take their sum. OK? So this works. And we basically tried, and we could prove some stuff unrealizable. And it kind of looks like what I showed you before, right? There is a precondition. There is a set of programs that I'm mimicking through non-determinism. And then there is a post-condition, which in this case is the output is not 1. But there is a caveat. And here is the first time things differ from traditional verification. What if I have 2 examples? There I only had 1. And this is the trickiness with quantifiers and the fact that the falsifying input may be different across programs. So when I build one instance of what I showed you before, the assertion fails if some program is correct on this input. If I build another instance with another input, that assertion will fail if some program is correct on that input. But unrealizability is that all programs are wrong on both inputs. So I need to make sure that when I falsify the assertion, so when the assertion is true, it's true for both. And so really, I cannot solve this problem separately by proving it for each example one at a time. I need to solve it in lockstep. And this is kind of what the encoding needs to be. I need to take my 2 inputs and basically kind of think of it in parallel. When I make my decisions with non-determinism, I evaluate both inputs at once to produce both outputs. Because otherwise, if I don't do that, I might get that each input is evaluated by a different program non-deterministically. So I want to make sure that they go to the same program. And so we did this, and that's how we built this tool. And basically, this is very simple. So this uses basically non-determinism to handle sets of programs and uses simultaneous execution to handle the fact that different inputs cannot go to different programs. And we built this in a tool, which basically it simply takes a Cygus problem, reduces it to a C program, and asks C-horn, can you verify it? And we were able to prove little things like you really need at least an if then else to do max. You cannot do XOR using only AND and OR, and some simple puzzles. OK? So, yes? Great question. For now, even forget about loops. We don't even have assignments. So we'll get there in a second, yeah. Yes, Moshe?
You have infinite set of program.
Yeah.
But there's always like one universal program, right? Choose I non-deterministically and run SI.
That's a great point. Yeah, so we could also do that. We can take the encoding of a program and then run it. And you can do that. That's another way to use non-determinism that in practice will not work. But you're right that I don't want to get to that. So we're writing a paper. This problem is slightly more undecidable than verification. So there is one more layer of infinity. So you cannot always do that because you still need to run also infinitely many inputs in the worst case. In this case, we only have finitely. But if you want to really verify for all...
No. I mean, the question is you put an arbitrary infinite sets there, okay? And of course, there are some conditions on that set. Okay?
It's a context-free grammar in this case.
I mean,
regular tree.
But in general, I need to behave basically the function from I to Si should be computable. Okay.
Correct. Yeah.
And if I have that, then I have a program that just run one of these programs, right?
I'm not sure I get the question, but if the question is like, is a problem computable? That's not what we're trying to solve. What we're trying to solve here is,
I can write a program.
Mhm.
When can I write a program? Normalistically choose I and run Si.
Mhm.
It requires the Si in some sense is computable from I. That's all I need. Otherwise, I just run I, deterministically choose when to stop, and I run Si.
So are you asking about the case in which you may not terminate? That's the part I'm a little confused.
I'm required, yes, this does.
Yeah. So for now, what I had here was all expressions.
Yeah.
So everything terminates. And we're going to get to that in a second, where basically what happens when you have non-termination. And things get harder for a couple of reasons, not just for that. But yeah, maybe let me get there, and then we'll try to talk about that. So the first thing we wanted to do, so this was only cygos, so only expressions. So there is no side effects. Forget about loops. There is actually no variables. And it's finitely many examples. So there are only finitely many inputs on which we run. So can we design something that is specific to this problem setting and doesn't use a C verifier? And so that's the next thing we did. And the idea here, so let's try to build intuition about how you will prove that a set of expressions are all wrong. So let's say I have this grammar. So this is x plus x plus x plus x plus x plus x plus 1. So it's basically 1, 2x plus 1, 4x plus 1. So this is the language of all the programs in this set. And let's say I want to show that on input 1, I want a program that on input 1 outputs 5 and on input 2 outputs 6. And I claim that there is no such program here because you can convince yourself pretty quickly that this thing always produces, given an even number, this always produces an odd number. Okay, so how do I formalize that intuition? And so at the high level, what I have is that if I run the programs in E, if I consider the set of outputs that E can produce on 1, 2, these are the corresponding sets. So I can do 1, 1, 3, 5. So these are the pairs of outputs that programs in there can compute. And what I want to prove is that the pair 5, 6 is not in this set. Okay, cool. So how do I do that? So this is where working with my colleague Tom Reps helps, because he is a living encyclopedia of everything that contains the word flow and analysis. And so he told us about this fairly obscure technique called grammar flow analysis, where the idea is the following. So let's say here I'm going to build, basically I'm going to build an invariant that E of 1, 2 is always a pair of odd numbers. Okay, that's kind of what I was trying to show. And the way you prove that is basically you build a set, given your grammar, you turn it into an equation, in general, a set of equations, that says this invariant is such that if I take this thing and evaluate them according to this abstract domain, in this case odd, odd, I get, so I'm solving this equation. And I'm claiming that odd, odd is a solution to this equation. And it's pretty easy to convince yourself because 1, 2 is odd, even plus odd, even is even, even, and even plus odd, odd is odd, odd. Union odd, odd is, join odd, odd is odd, odd. Therefore, this is a solution. Therefore, this is an invariant. And therefore, 5, 6 cannot be in it. Okay, 5, 6 cannot be in odd, odd. And so we automated this proof technique. And you can automate it for various domains. It's not always possible to solve these equations. But once you put the problem in this setting, here comes something that some of you will appreciate. We basically also proved that these equations could always be solved for linear integer arithmetic, even with conditionals. So if you have finitely many examples that you're trying to prove unrealizability, and you have a grammar of LIA or conditional LIA terms, you can actually exactly solve those equations, which means the problem is decidable. So if you have a grammar of LIA or CLIA terms, and you have a set of examples, and you're asking, can there be a program correct on these examples? We prove that the problem is undecidable because the equations that come out of grammar flow analysis can be solved. And so this was surprising at the time, and this was kind of a nice case where ditching the C-style verification led to some also interesting theoretical insight. And it also ended up working much better. We were able to basically become faster on every benchmark and solve new stuff. OK? Questions? Yes?
Just computing terms?
Correct. Here we're at terms level. only terms. So now we have 10 minutes, and we're going to go to side effects and start doing the real deal. Okay? So imperative programs. So let's say we have now programs that can have variables that can change their values when we produce them. So similar example to before. So before we had this, so the nice thing about terms, about expressions, is that the value of variable doesn't change. There is no side effect. So it's like whenever I see x, I can just replace it with 1, 2. Their corresponding value. In this case, the examples are 1 and 2. Therefore, x is always 1, 2, no matter where I find it in the program. So this is the property of expressions. They have no side effect. But if I have statements like this, now we're in trouble. Okay? So this is a grammar that accepts imperative programs that basically compute 2 to the n, right? So, and I want to show that on x equal 1, I want to produce x equal 5. And you can convince yourself that that cannot happen, right? Because this program can produce x equal 1, x equal 2, x equal 4, x equal 8, and so on. So now if we try to do the trick that we did before of building an equation, we are in trouble. What happens? I basically get, OK, what are the output states that I can produce on x equal 1? Well, it's 1 plus 1. But now I need the outputs on the next value of x, which now is x equal 2, because x has changed, right? OK, no problem. I'm going to add another equation. Oh, but now I need 4. And so basically, I get stuck into this computing all the possible outputs. And I cannot build a finite set of equations. So you can. Actually, it looks like you cannot, but really you can. The problem is that we're only looking at outputs. But when you talk about imperative programs, you have to talk about inputs and outputs at the same time. You need to talk about how the state changed. You need to talk about relations. And so that was the first kind of mini discovery. You really need to build a relation, an inductively defined relation in this case, such that this relation contains all the possible inputs and outputs of all those programs. And now what you want to show is just that the input-output you want is not in this relation. And I'm not going to go too much into details, but the way you solve this using something like an SMT solver is to go beyond SMT. And you need this thing called constraint Horn clauses. So if you don't know what these are basically SMT plus fixed points. It's sort of like plus least fixed points. So this is like data log. If you're familiar with it, it's like data log plus SMT theory. I'm kind of being a little sloppy here, but just to give you some intuition. And it turns out that even this is not enough. And here is the second insight. So the first insight was like, we need to track all inputs at once. We cannot send them separately. Here is the next insight. So if you are going to get anything out of this talk, this slide is the one you need to pay attention to. Okay? So if I see some people are starting to get into the 2 p.m. phase. So wake up for a second, and this is the important part. So let's say I have these 2 programs, x plus equal 2 and x plus equal 3. So the semantic relation of these 2 programs, so basically the input-output relation of anything derivable from A is the following. So on input 0, I produce 2 with the blue one. On input 0, I produce 3 with the green one. But I can only pick one of these programs. Remember, I'm trying to prove properties for all of these programs. So now let's say I want to prove something about what happens when I repeat one of the programs in A twice. So you will think, oh, I can just take the product of this relation, right? But no, you cannot, because if I do that, I start mixing and matching the relations of different programs. So in particular, I'm allowing to do x plus equal 2 and then x plus equal 3. And that will be incorrect reasoning. Because, for example, a property of these sets of programs is that given 0, it always produces either an even number or a number divisible by 3. No. Repeat A twice is the grammar of program. This is a grammar of programs that contains 2 programs. Repeat x plus equal 2 twice and repeat x plus equal 3 twice. It's a grammar of programs. It's not one program with non-deterministic choice. It's a grammar of programs. That's crucial. So this is a set of 2 programs that should only contain 2 programs, one where the body is this and one where the body is that. And so we call this the shifting sense problem, where basically this is where all verification fails if you don't do things correctly. So you basically, how do you track that the body of a loop, or in other cases can happen, doesn't change across iterations? And so So here, if we do this is on sound, so the trick is that actually the relation cannot even just capture the input and output. Even that is not enough. We actually need to remember which program produced them. And you can bypass this with some extent. So really, you can, instead of the program, you can have the actual function implemented or relation implemented by the program, but you need to remember who did this, which program contributed this relation. So we did this, and we basically used constraint or clause solvers to prove a bunch of cool things. I'm not going to get to the detail, but we built an unrealizability checker for sort of everything, that because it can handle sort of everything, it doesn't handle much in practice. But the idea is that if you have examples and you have a grammar of imperative programs, you can build a query using constraint or clause solvers, send it to a tool, and we could prove pretty cool things like you cannot swap two numbers if you don't have an auxiliary variable and you don't have XOR. You cannot compute the XOR of two variables, no matter how many loops you have, if you don't have something that can change the value of bits, and a bunch of other things. So this is, when I say we can prove this, I mean automatically. We just push, and you get the proof. And here is the part. I think I have 5 more minutes. OK. I just took 5 more minutes. So here is the part where I lie to you until now. I say you get the proof. But I never gave you proof. I just gave you a result. So I just say you push, you get unrealizable, and you celebrate. But we want a proof. What is a proof? And here, I think, is like the interesting part. So when we were doing this CHC-based solving, you need to understand the details. But somewhere, this solver, when we started digging through the lemmas that it had computed to prove unrealizability, we found something like this. So here we were trying to prove that none of those programs, you're trying to show that you cannot do XOR using only AND and OR. We were trying to show that none of these programs on the input 14, 15, output 1. So the XOR of 14 and 15 is 1. OK? And this is telling you, hey, I'm going to tell you this is a theorem. For every term in this grammar, it is the case that 14, 15 always spits out something such that the third bit of X prime is true. So this spacer, the CHC solver, magically came up with this fact. And we were like, we like that. We want more of those. So that's a proof to me. That's an invariant. And it's an invariant, but not a usual invariant. This is an invariant about sets of programs. Okay? So this is a property that is not true for multiple loops, for multiple whatever. This is a property of all programs in a set. And so the solver somehow was able to do that. And so we got really excited. It's like, OK, so really proving unrealizability, it's all in the same way proving that one program is correct is about finding pre, post-condition, and loop invariants. Proving unrealizability is about finding sets of programs invariants. So invariants that are true for sets of programs. And Jimbo then basically built a logic, very much like Hoare logic, like where you can prove things like this. So so the idea here is in normal Hoare logic, you say, if I'm in P and I run S, I get something in Q. It is if I'm in P and I run one of the S1, I get this, another of this one, I get this, and so on. As long as they're all in Q, this is a proof. Basically, proving a triple like this boils down to proving unrealizability. And I'm not going to go into the details, but the point is that we have a bunch of rules, very much like in Hoare logic. So in our case, for example, the rule for sequencing two sets of programs is basically is a proof for the Cartesian product of these programs. And the rule looks very much like the Hoare one. I'm going to just show you sort of how that invariant that we saw built by Spacer can be used to build a proof in this logic. And so let's say here I want to show, this is a simplified example. I want to show that if x is equal 1 and y is equal 3, the output is always odd for anything in here. That's kind of the last bit is 1. And the way you prove this in this logic is that's what I want to prove. So I want to prove it for E. But when proving it for E, I will be required to reason about E itself. So I'm going to start assuming this as an inductive hypothesis. So this is assuming that this invariant is true, can I show that this stays true? And so for example here, let's get to the specific point. For example, to prove that it is the case that on x equal 1, y equal 3, v is odd, it's a trivial application of weakening and the variable rule. Because x is odd, x is 1, therefore is odd. And then in the other cases, you get inductive hypotheses from the children. And here you get, because this is odd and this is odd, the end of two odd things is odd, and therefore you build the proof. So what's exciting about this is that this decoration of the grammar, it's a proof, meaning that I can locally check it using your favorite SMT solver or whatever. So I'll conclude. It's much more complicated. So it turns out that you need to increase the logical power quite a bit to reason about sets of programs. In particular, you need to go through infinite vectors or infinite arrays if you want to actually be able to always prove things. And we have some soundness and completeness rules. We got it wrong at first, but then we fixed it. And I'm going to just show you, as the last example, one case where, in fact, everything I showed you so far, you can prove it unrealizable with 1, 2, 3, 4 examples. But this is an example where you need infinitely many inputs to show that the problem is unrealizable. So this is the grammar as basically a bunch of if then else's like this. You can say if x equals 0, then 0. Or you can say if x equals 2, then 2. If x equals 8, then 8, and so on. And I want to show that this grammar cannot implement the identity because it only has constants. It cannot say output x. It can only say if x is equal to 1, output 1. If x is equal to 2, output 2. So the thing here is that no matter how many inputs you give me, I can always build the program that just is correct on all those inputs. It has n if then else's and outputs the corresponding number. And if you want to prove this, so we were actually able to automate this proof, you need basically this infinite theory of array. The array are infinite arrays where you say, assuming I start with the ith entry of my array being I, no matter what program I run, I end up that some entry doesn't have I anymore. Basically, I'm not implementing the identity. OK, so in a couple of weeks, we are going to update this in archive probably. But we have a paper now on automating this logic. And we actually have a theoretical result that shows that these infinite vectors are needed. You cannot get away with it. It's just the semantics is not enough otherwise. OK, lots of stuff. People gave money. Thank you. And these are the people who did the work.
Let's thank Loris. Questions?
So thank you. I'm thinking about synthesis of ongoing behaviors, so
Yes.
things like LTL. And in LTL, we use determinacy of games, that if a specification is not realizable, then the negation of it is realizable by the environment.
Mhm.
And if I cannot synthesize a transducer, I can synthesize a transducer for the environment that would provide, that will win always.
Mhm.
So this transducer will show me that actually I can give outputs that that wouldn't work. Are there similar things in
Yeah, so
your
in a
area?
way, this is, I mean, maybe let me take a step back. It's like, let's go to normal verification. It's like, the thing is like, realizability in normal verification, we don't call it realizability, we call it correctness. Correctness is building a proof, which a proof is basically a game in which no matter what you do, I can show you that it's correct. And realizability is testing in which you give me an input in which I'm wrong. And so now we are in synthesis and realizability for LTL, you're lifting kind of to this infinite game. And so the proof itself needs to be a strategy because it's an ongoing game. It's just this is the normal exists for all game, so it only has one turn, right? So in my proofs are the one turn of the unrealizable player. And the realizable player victory is giving me the program. So the reason it's just two different type of proofs, right? One is a witness.
Yes, but
Yeah.
it's kind of a special case. If it's only
So
one
if
round.
you want to do the full dual, we're also working on that. So we don't have results, but really the dual of these is building kind of the version space of all the correct programs, because this is already all of it. Like this is all of unrealizability. Like I just proved that it's on every input. You're wrong, and you're right that what we haven't done much is the solution to a synthesis problem is one program, but it could be all the programs that are correct. And so the interesting duality that is here, and actually somebody submitted, I saw a paper on archive, would be to take incorrectness logic, which is now the dual of our logic for showing that multiple inputs lead to a buggy behavior, and turn that into the dual of this logic, which is here is a set of programs that are all correct on this behavior. So I think that's the duality I can see. But the game itself, that's a matter of turns due to the repeated behavior.
Great, thank you.
Yeah, no problem.
Yes, thank you. So you went to higher order with your assumptions in the sense that array is a higher order object.
Correct. Lambda terms, if you want.
Yeah. There are many questions, but can you handle many loops?
Yeah. So we're
like grammar with loops as a construct in a grammar, not the outside. As you had on your examples, it was like you had while only once.
Yeah. So this logic I presented to you is, okay, now it's, how do I say? In the paper we published, it's actually incorrect. So the rule for loops is unsound. So it's sound but incomplete. It works, you can handle loops, but so the logic we have is sound and complete for programs without loops. And this result is that actually we just realized, so it is sound for loops, but it's not complete. To get a complete rule for loops, this is a proof you need lambda terms. It is the
so
least.
You need to go higher and higher.
Yeah, you need to, even not for one loops, for as many loops as you want. So this is even for unbounded number of loops. But this is it's actually that example I gave you is sort of the counter example that if you don't remember who produced what, you're basically, you cannot recover it.
Last quick question. Is it quick? Did you? Yeah, okay.
Don't you run here into the Skolem problem on linear recurrences, which is not even known to be decidable?
Oh, decidable? Oh, we never worried about that. That was the starting point was that the problem was undecidable already to start with. Actually, it's already undecidable without loops and without, so you already, if you have, okay, it's already undecidable if you have Cygus plus specs, it's already undecidable. If you have, even with examples that we show is decidable, so LIA is decidable. If you add X equal, so if you add assignments without adding loops, this feels like it should be decidable. But if you remember that even just with assignment, I started creating squaring behavior. I didn't actually add, I was still in LIA in terms of terms, but because I was doing X equals X plus X, X equals X plus X, that causes squaring. And you can very easily, I mean, I can sketch it on the board after the talk, but it's like, you can reduce to counter machine already to that. So it's very, very quickly. You don't need, you need one example and X plus equal X. That's it.
Okay, let's thank Loris. Thank you, Loris.